For this project, we will be working with OpenCV. OpenCV stands for Open Computer Vision Library. So let's start coding by import CV2, and we need to import numpy as well. So import numpy as nb. Now if you haven't installed OpenCV, you can install it from the command prompt using the command pip install OpenCV Python. Now in my case, the requirements are already satisfied, so I'm moving on with the code. So the input for this project will be a stream of frames that are captured by a video capture device such as our webcam. So let's define VC equal to cv2.video capture of 0. Now I gave the parameter 0 so that it will use the first camera in the system, and in my case it is my webcam. So if you have a second camera, you can give the parameters 1. Now the entire project can be broken down into 3 major steps. In the first step, we try to capture an image of our background. In the second step, we try to find an approximate color range that can represent our cloak in HSV color space. In the third step, we replace all those pixel values for each frame if the pixel value falls in the specific range that we found in the previous step, and we replace it with the pixel value from the original background image. So let's just type step 1 capture background image, step 2 HSV color range for cloak, and in step 3 real-time application. We can access the frames that have been captured from our video capture device using vc.read, and we can display those frames using cv2.imshow. In order to keep on displaying those images until an interrupt is provided, we can use a while loop. So let's say while cv2.wait key of 1 equal to -1. So cv2.wait key of 1 waits for 1 millisecond, and if there isn't any key interrupt, it returns -1. So the while loop will be executed as long as there isn't any key interrupt. Return value comma frame equal to vc.read. Now return value can be used to check whether our video capture device is working correctly or not, as it returns a boolean value of either true or false. It returns false when our video capture device is unable to start or encounters any other problem. So we can also write frame equal to cv2.flip of frame and axis of 1. Now I wrote this line of code to avoid any confusion caused by lateral inversion. That is, left becomes right and right becomes left. We can also resize our frame. So let's write frame equal to cv2.resize frame comma 1280 comma 720. Let's display our frame using cv2.imshow, and I'll give the window name as frame, and let's display our frame. So this while loop will be executed as long as there isn't any key interrupt. So our objective is to capture the background image. So in order to do that, we can save the final frame as our background image. So let's write cv2.imwrite background.png comma frame, and this will be the final frame after execution of the while loop. Let's give a print statement before that. print press any key once suitable background has been obtained. And finally, we need to write cv2.destroy all windows, and at the end we need to also include vc.release so that we release our video capture device once our project has finished execution. So let's try to compile and execute our program. So I need to turn off my screen recording in order to use the webcam. And let's add another print statement here. So print, so let's give /n/n/t/t background image has been saved successfully. So let's go ahead and execute it once again. So our program is working, and I'll just remove myself from the background, and I'll just press the space bar, and our program has terminated successfully. Just ignore this warning. So here we can find our background.png along with our Python file. So let's take a look at it. Now in stage 2, we can apply color detection for identifying our invincible cloak. So let's do that as a separate module. So I have created a new file called calibration.py, and you must note that the C in calibration is a small letter. So let's import OpenCV, import CV2, and import numpy as NB. So let's create a function calibration, def calibration, and you must note that the C in calibration is capital for the function. So let's define our data input stream as vc equal to cv2 dot video capture of 0. Now let's define our window, and we can do that using cv2 dot named window. Now this window will be used for adjusting our HSV values, and I'll get to the HSV values a bit later, for identifying our invincible cloak or the cloak that will be used as our invincible cloak. So cv2 dot named window, and we need to give the window title. So let's give it calibrate HSV. So this window will be helping us to identify our HSV color range for the cloth that will be used as our invincible cloak. We will be converting our frame captured from the video capture device from BGR format to HSV format, and HSV stands for hue, saturation and value. Since we can define a range of colors in HSV format, so we need to define 6 track bars, 3 for the lower HSV values and 3 for the upper HSV values. So let's add our track bars as cv2 dot create track bar, and we need to provide the name of our track bar. So the first one will be L underscore hue, it stands for lower value of hue, and we need to provide the name of our window, so calibrate HSV, and we need to provide the range of values. So hue varies from 0 to 179, a total of 180 values, and MD. So let's define our MD function, def MD pass. I gave an empty body to our empty function as we do not require any action to be taken on change. Similarly, we need to create 5 more track bars. So the second track bar will be L underscore sat for lower value of saturation, and the value varies from 0 to 255, a total of 256 values. And the third one will also range from 0 to 255, and it is lower value of value, so L underscore val. And the last three will be upper value of hue, upper value of saturation, and upper value of value. So our saturation and value varies from 0 to 255, and our hue varies from 0 to 179. We can define default values for our track bars using cv2.set track bar pose, and let's provide the name of our track bar. So u underscore hue calibrate HSV, and the default value will be 179, which is the maximum upper value. And let's copy this 2 times for our upper value of saturation and our upper value of value. So upper saturation and upper value, and the default values for upper value saturation and upper value of value will be 255. We can display our window similar to how we displayed our frame using an infinite while loop. So while cv2 dot wait key of 1 equal to -1. So this while loop will be executed as long as none of the keys were pressed, and wait key of 1 waits for 1 millisecond and returns a value of -1 as long as none of the keys were pressed. Frame equal to nb dot flip of frame comma 1. cv2 dot imshow frame comma frame. Now this will help us to visualize how our frames will be affected on changing the values for each track bar position. So let's convert our frame from BGR format to HSV format. So we can do that using cv2 dot convert color of frame comma cv2 dot color underscore BGR to HSV, and let's store the resulting image in HSV. Now we need to provide a color range for the cloth that will be used as our invincible cloak. So let's define lower as lower equal to list of L underscore hue, L underscore sat, and L underscore val, which are the lower values for hue, saturation, and value. And we will be getting these values from our track bars. So let's define upper value of hue, upper value of saturation, and upper value of value. Now we can get the value that has been adjusted in our track bar using cv2.getTrackBarPose. So let's define L underscore hue as L underscore hue equal to cv2.getTrackBarPose L underscore hue, and the name of our window, so calibrate HSV. And let's copy this line and paste it 5 more times. So lower value of saturation L underscore sat, lower value of value, now we need to provide upper value of hue, upper value of saturation, and let's paste it once again. So upper value of value. So now we have our color ranges defined, and we can now apply our mask. So we can do that using mask equal to cv2.in_range, and we need to pass our HSV formatted image. Then we need to pass the ranges as a numpy array, so nb.array of lower and nb.array of upper. Now we can display our mask using cv2.imshow, and I'll give the window name as calibrate and mask. Now outside the while loop, we need to add vc.release to release our video capture device, then cv2.destroy all windows, and finally we need to return our lower and upper HSV values. So return lower comma upper, and let's call this function from our original invincible cloak.py file. So first we need to import it. So from calibration import calibration, and for this line of code to work, you must ensure that your calibration.py file is located in the same directory as your invincible cloak.py file. And so lower comma upper equal to calibration. So let's add a print statement. So print lower comma upper, and let's add a print statement here. So print press enter to start calibration. So literally calibration is the same as color detection, and here we apply color detection for identifying the color ranges of the cloth that will be used as our invincible cloak. We need to make a small change, and so the function md will take one positional argument. So let's define md as def md of x. So after saving our calibration file, let's compile and execute the Python file. So let's skip our background image and press enter. So we have got the window containing our 6 track bars, and we have got our mask right here. So yeah, and I have got my blanket here, and I'll be using this blue blanket as my invincible cloak. So let's try to adjust the values. So first I'm going to adjust the value of the lower value of value, and now let's see the lower value of hue. So you can observe that it's pretty hard to come up with a definite range of HSV values that can eliminate noise. And to avoid noise, we'll be working with morphological transformations on our mask. So let's close this. So let's go back to our calibration file, and we can define a new function and call it transform. So def transform, and it will take our mask as the input. And for morphological transformations, we'll be working with erosion and dilation. So erosion takes a slider, and for each pixel, it will change it to the color of its majority of its neighbors. And dilation does the exact opposite. If a pixel contains a color that is not equivalent to the color of its majority of neighbors, then it turns the color of its neighbors to the color contained by that pixel. And you can understand that when we execute the program. So we need to first define our kernel, which is the slider. So kernel equal to nb dot ones of 10 by 10, and I'll give the data type as nb dot uint 8, which stands for unsigned 8 bits, unsigned int 8 bits. And the next thing we need to do is to apply our erosion and dilation, and we can do that as mask equal to cv2 dot erode mask, and we need to provide a kernel and the number of iterations. So I'll provide the number of iterations as iterations equal to 5. And now we can move on to applying our dilation. So mask equal to cv2 dot dilate mask comma kernel comma iterations equal to 8. Now I gave the number of iterations for dilation more than the number of iterations for erosion, as we often tend to remove the boundaries of the blanket when we set our lower and upper HSV values from the track bars. And this is because the color of the blanket tends to be different at the boundaries than at the center due to effects caused by lighting. Now we can return our mask, and before that let's just show the input mask cv2.imshow and mask. So here we need to add another line, mask equal to transform of mask. And in our so let's save the file, and in our invincible cloak.py we need to import the function transform as well, and we'll be using that in our third stage. So now in the third stage we'll be working with real-time application, and for that we need to get our data input stream, and for that I'll just copy the while loop here. So while cv2.wait key of 1 equal to -1, we get our return value and frame, and we need to flip the frame and we need to display it. So cv2.imshow, then we need to convert it to HSV format, and we do not need these lines of code here. So get our mask using cv2.inRange by providing lower and upper, and we have got our lower and upper by calling the calibration function in stage 2. So we have applied mask equal to transform of mask, and then cv2.imshow of calibrate comma mask. So all we have done until now is take an input frame, then apply a range of HSV values to find our mask, and then apply morphological transformations on our mask to avoid noise. So we do not need this line of code here, as we already have vc.release, and we can move this line of code here. We can obtain the portion of our background image defined by the mask using cv2.bitwise and. So let's go ahead and cv2.bitwise and background, and I'll define background in a moment. So background and mask equal to mask. So Let's define background as background equal to cv2 dot imread and background dot png, which is the same image that we obtained from stage 1 of this project. And let's store the image returned by our cv2.bitwise and in a temporary variable. So temp equal to. Now we need to get the portion other than the portion defined by our mask for each frame in real time. So first we need to apply bitwise node to our mask. So mask equal to cv2.bitwise underscore node of mask. Now we can get the region defined by the new mask using frame equal to cv2 dot bitwise underscore and of frame comma frame, and we'll use the new mask. So mask equal to mask. Now finally we can combine the two regions using cv2 dot add. So let's define the new frame as frame equal to cv2 dot add frame comma temp, and finally we can show this image. So cv2 dot imshow frame comma frame, and we do not require this cv2 dot imshow here. And we need to add another line here, frame equal to nb dot array of frame. This will convert our frame to a numpy array. And since the message I have printed here is press enter to start calibration, we can change this from a print statement to a input statement. So let's just define a variable c. So c is equal to input of press enter to start calibration. And let's change this to frame equal to cv2 dot flip, and we can resize our frame. And for that, let's just copy the line of code from our stage 1, and we do not need this imshow here. And another thing that we can do is to define our video capture device again. So let's go ahead with that. So before that, we need to release the first instance of our video capture device. And let's print statement c equal to input of press enter to start magic. So let's go ahead and execute our project. So the first stage is obtaining the background image. So yeah, now we can start our calibration. So we have two masks. One is the original mask and the other one is the mask after applying morphological transformations. So I have got my blanket here, and I'll be using this as my invincible cloak. So I'll start adjusting the values. So now we can move on to the third stage, which is real-time application. So let's try to see if our invincible cloak is working. So that's it for this project tutorial. Thank you.